Hello.
Hey, good afternoon, everyone.
Great.
We are ready to get started. So my name is Jessie Mongeon. I am a technical writer at DFINITY. DFINITY is the foundation that is one of the primary contributors to the Internet Computer. As a technical writer, I spent a lot of time doing things like developer documentation, creating different educational resources, doing educational videos and presentations like this one. And today I'm excited to give this presentation and workshop on using ICP as a Bitcoin layer 2, part 1. In today's part 1, we are going to get an introduction to ICP and the Bitcoin integration that ICP has. And then we're going to take a look at a demo of how we can deploy in a canister locally and have that canister interact with a local instance of the Bitcoin network to demonstrate how a canister smart contract can send and receive Bitcoin, have custody of that Bitcoin, and also query different information about the Bitcoin network. So what is the Internet Computer? The Internet Computer is a permissionless, secure compute platform that is built using blockchain technology. So it's a little bit different from some of the other blockchains that are out there in the sense that everything on the Internet Computer is on-chain. There is no need to outsource things like compute or storage. Everything is able to be run completely on the Internet Computer on-chain. So the way that ICP works is nodes are able to run the ICP replica software, and a node is simply a piece of hardware that's running the software, and it can be located in any data center across the globe. We have hundreds of different data centers that operate our nodes. Each node is operated by an approved provider. So we are not a traditional network in the sense that Ethereum, you can go to Ethereum and download the Ethereum software and run an Ethereum node, and same with Bitcoin, you can mine Bitcoin on your home PC if you want to. So that's not how our network works. We have very high standards for our node providers to help support the standard of compute and storage that we provide our developers and our users on the network. And so if you want to be a node provider, you need to meet these high standards and then also be approved through our network's governance system. And then once if you have a node running, or if you interact with a node, that node is going to be part of a subnet. So a subnet is a segmented portion of the blockchain. Each subnet is either going to be 13 or 34 nodes, and they're going to run their own consensus separate from other subnets. And each subnet can talk to one another. They are not segmented in the sense that they are unaware of the rest of the network. They are all interoperable, and if you have a node on one subnet that is running a canister, it can talk seamlessly to any other subnet running any other canister. Every node on each subnet runs a copy of each of the Canister smart contracts that are deployed to that subnet. So if you deploy a smart contract to a 13-node subnet, it's automatically going to be replicated 13 times. You don't have to do any manual replication or have any specific setting for that automatic redundancy. And each smart contract is going to use the subnet's collective resources. So it's going to use the subnet's compute and storage. There's no need to use external compute or storage or any other resource. And each smart contract pays for its own resources. So this is what we call the reverse gas model. In other chains like Ethereum or Solana, when you interact with the chain as the end user, you pay the gas fee from your wallet when you make a token transfer or interact with an application. But on ICP, if you're interacting with a dApp, you are not responsible for paying the gas fees that dApp is using. The developers of that smart contract are paying the gas fees on the back end. And smart contracts on ICP are 100% on-chain and decentralized. So I keep using this term canisters. What this means is our version of a smart contract. You can think of this kind of as an evolved smart contract because it has things like on-chain compute and storage, and it's also configured a little bit differently from other traditional smart contracts on other chains. So our smart contracts are all going to be compiled into WebAssembly, and then they're going to have a WebAssembly state that is running alongside the code for that canister. So this means that you can write a smart contract canister in any language as long as you can compile it into WebAssembly. So you don't have to learn our in-house language Motoko. You can write things in Rust, JavaScript, Python. And then once you deploy your smart contract, if it's just a backend smart contract, it's going to be on chain. But if you want to have the front end of your application that is written in React or some other framework, you can write this as a front end smart contract and have that deployed on chain as well. And then all of your application data is automatically going to be on chain with that. And all of the front ends are going to be hosted on the web by default, so you don't have to set up any special routing or domain configurations. You can deploy to the mainnet and automatically get a public URL. You don't have to do any special web hosting that you would do with a traditional application. ICP also has some really incredible unique features. A couple of these are some of our cryptographic features like threshold signatures or chain key cryptography. We also have on-chain randomness, timers and heartbeats. We have what are called HTTPS outcalls, where a smart contract on ICP is able to obtain data from any source on the web, not just another Web3 source, but any Web2 API it can pull that data from as well. We also have decentralized governance, not just for ICP itself, but we also have a protocol version of that called the SNSs, where if you have an application deployed on ICP and you want it to be controlled by a decentralized government system, you can have it be handed off to an SNS, and then it's managed by the community of the application. And lastly, the big one that we're here to talk about today is this chain fusion term. So what is chain fusion? Chain fusion is ICP's ability to connect directly to other blockchains without a bridge or an oracle. This is made possible by our ability to have decentralized bidirectional communication with other chains. Right now, we have this with Bitcoin, Ethereum, and EVM compatible chains, and soon Solana. Canisters on ICP can call smart contracts on other chains. They can also call the block information from other chains, the gas fee information, any of the other queryable information about Bitcoin, Ethereum, or those other EVM chains. We can query it, and then we also have the ability to obtain data using HTTPS outcalls for chains that we don't have current integrations for. So things like Base and Arbitrum, our Canister smart contracts can still query information from those using HTTPS outcalls. And chain fusion enables use cases like a decentralized borrowing protocol, a multi-chain DEX, a multi-chain wallet, spreading asset liquidity across different chains, or creating marketplaces for cross-chain assets. We're seeing some of that for things like ordinals and runes on the Bitcoin side of things. So talking specifically about our integration with Bitcoin, ICP is able to act as a Bitcoin layer 2 in the sense that an ICP canister is able to have Bitcoin addresses. They're able to receive and hold Bitcoin directly on the Bitcoin blockchain. They're able to access the balance and the UXTO set of the Bitcoin addresses. They can access block headers on the Bitcoin blockchain, and they can also securely sign and submit Bitcoin transactions. So they essentially act as if they are users directly on the Bitcoin network rather than Canister smart contracts deployed on ICP. So how does this work? So our integration with Bitcoin is a direct integration. So what this means is that we have an on-chain canister known as the Bitcoin canister, and this holds ICP's on-chain Bitcoin state, which is the UXTO set, the most recent Bitcoin blocks, and then any current outgoing transactions from ICP that are being sent to the Bitcoin network. And we are able to facilitate these transactions through chain key signatures, which are our in-house unique cryptographic protocols for secure distributed key generation and periodic key resharing. We have threshold ECDSA and threshold SNOR. We'll talk a little bit about threshold ECDSA in this presentation, but the second half of this workshop that will be on Thursday is going to dive deeper into these chain key signatures specifically and talk about threshold SNOR and also taproot signatures. And so we have the Bitcoin canister, but then how does the Bitcoin canister talk to the Bitcoin network? We have a Bitcoin adapter, which connects directly to the nodes of the Bitcoin network. It functions similar to a traditional Bitcoin node. And so any pending transactions are submitted to Bitcoin through the adapter after every round of consensus. So that term threshold ECDSA that I mentioned, this is a novel chain key cryptography protocol that we have, and every subnet is able to query the nodes that enable threshold ECDSA. And so there are only a few subnets that have threshold ECDSA enabled, but if you are deploying a Canister on a different subnet, you can still query the threshold ECDSA method from what we call the management canister. And on the subnets that have threshold ECDSA, they are holding a shard of the private key for that subnet. And more than 1/3 must agree in order to generate a signature. So there is a bit of consensus that happens in that regard. And then each canister can control an unlimited number of public keys to sign transactions with threshold ECDSA. And so what this cryptography protocol enables are the ability to generate P2PKH addresses, which are the addresses that allow canisters to natively hold Bitcoin. And then threshold ECDSA is also used in the Ethereum integration and the integration with other EVM chains. And then if there are other blockchains that use ECDSA as the signature scheme, we're able to communicate with them through this as well. And it also enables things like a decentralized certification authority. So when a canister wants to sign a Bitcoin transaction, they are going to make a call to this canister method of sign with ECDSA. And so like I mentioned, this method is part of the management canister that just kind of serves as a system API on the ICP network. And so any canister can call this, and then once they call that, the transaction is sent to the Bitcoin network through the Bitcoin canister, and then that canister will submit it to the Bitcoin network through the Bitcoin adapter. And then in the opening presentation that we went through before this, and we were talking about some of the bounties, we heard this term CKBTC, and we saw a brief overview of it, but to give a little bit more information about what CKBTC is, it is a chain key token. So this is a more secure alternative to wrapped tokens. It uses that chain key cryptography, including threshold signing, in order to create that security. Each chain key token that is deployed on ICP is backed 1-to-1 with the native token that is held on chain in an ICP smart contract. So all of the CKBTC that is currently minted and in somebody's wallet, there is a 1-to-1 backing for that is being held in a smart contract. And there are no intermediaries or centralized bridges that are used for chain key tokens. It is all a decentralized process. CKBTC was the first chain key token, and then we added CKETH, and then we also have CK ERC20 tokens. So these are tokens that support the Ethereum ERC20 standard, and some of these include CK Pepe, CK Doge, and CK USDC. So now that we have kind of some context for what ICP is, how it works, and how the Chain Fusion Bitcoin integration works a little bit, we're going to go through a demo of building with Bitcoin, and we're going to take a look at how we can deploy a Bitcoin dApp locally. So we're going to first set up a local instance of the Bitcoin network, and then we are going to deploy a Motoko canister that creates Bitcoin methods that we can use to send and receive Bitcoin in that local Motoko canister. So what we'll learn is how to run an instance of the Bitcoin network, then also run the local ICP replica that is going to communicate with the local Bitcoin network. We're going to use threshold ECDSA to generate a Bitcoin address for our local Motoko canister, and then we're going to use that canister to send and receive Bitcoin locally. And of course, since this is all local and testing environment, it won't be real Bitcoin, it's just going to all be fabricated Bitcoin.
And then we're going to begin by setting up a local Bitcoin network. This is because to develop a Bitcoin app locally, we're going to need a local instance of the Bitcoin network to be running that we can interact with. This is useful because the local network allows us to mine blocks quickly and facilitates testing without having to rely on the Bitcoin testnet or Bitcoin mainnet. So to get started, we're going to first download the Bitcoin core. For Mac users like myself, it's recommended to use the .tar.gz file. So we're just going to open this up and download our Bitcoin core. It looks like the latest version is 27. So we're going to go ahead and download that. And we can see that that got downloaded. And so then we are just going to move that from our downloads, and that's the Bitcoin core, and we're just going to move it to our current working directory. So now we can see I've got that Bitcoin package, and it looks like I actually have the zip one that got downloaded automatically. So let's just go ahead and make sure we get that correct tar.gz one instead. Let's see, did that give it to me? Yes, okay. So let's just okay, so now we've got that tar one instead. And so now we are going to unzip it with tar, and we're going to use the XFZ flags and then the name of that package. And it looks like it didn't like my Z flag. So let's just use X and F. Now we're going to navigate into that new Bitcoin, and it looks like the latest version is 27. And while we are in this, we're going to create a new directory called data. And then we're going to open up the bitcoin.conf file. So I'm just going to open it up here in VI. And it looks like there's a lot of stuff in here. So we're going to actually close that. And I'm going to open it up in VS Code so we can take a better look at it. So I'm just going to open my developer journey and this Bitcoin folder, and then open up this bitcoin.conf. And let's see, we're going to insert this at the beginning of the file. So I'm just going to go ahead and copy that entire section, and we'll get this fixed a little bit. And so after these first couple of lines, we're going to go ahead and insert this, and then we're going to use Command S to save that. And so what this does is it enables reg test, which is required for local private Bitcoin network instances. Reg test is short for regression testing mode. It's going to set some test credentials that are going to be used by the local instance for authentication. And so then we are ready to start our local Bitcoin instance. And so we are going to use the /bin/Bitcoin D. Then we're going to give it the conf flag, and we're going to have that equal the current working directory with pwd. And then we want that conf file to be bitcoin.conf. And then we want data dir or data directory. We want that flag to equal the current working directory /data. And then we want to pass the flag port, and we want 18444. So I'll press enter, and we're going to see that Mac is going to give us this error saying that it cannot be opened because the developer cannot be verified. And if we go into the little help menu with the question mark and then open privacy and security settings for me, we can scroll down and hit cancel. And then let's try and run that again. And let's see, privacy and security. And here that we scroll down, we can see Bitcoin D was blocked because it's not from an identified developer. We're going to allow that anyways. So then we'll close all of this. And then go ahead and now when you go to run it, it'll ask you if you are sure you want to open it. And we do want to open it. And it's going to ask if we want the application to accept incoming network connections. And for this, we're going to click deny since we don't want it to accept outside network connections. We're just looking to use the reg test local network. So we're going to hit deny. And we can see that it took up the entirety of our terminal output. And we can see that it was able to spin up a local Bitcoin instance with a local network. So now we are going to need to open a new terminal window. So I'm just going to open a new window. And we're going to keep that Bitcoin one running in the background. And I'm just going to open this up. And we'll keep a little output at the bottom. Well, actually, we'll put them side by side here. That'll work. Okay, so next we are going to clone the basic Bitcoin example from the DFINITY examples repo. So I'm just going to copy this git clone and this cd command from the tutorial. And in my instance, I already had that examples repo already existing, so then it just navigated me into that existing basic Bitcoin one. So now we're going to start a local instance of DFX with DFX start clean background. And we're going to see that our DFX local replica is going to automatically connect to the local Bitcoin adapter. And we're going to see that the Canister Bitcoin integration gets installed and some other output about the local Bitcoin integration running. And so the output of this is also going to take up the terminal window. So now we have the Bitcoin terminal and the Bitcoin integration terminal. So we're just going to make both of these a little bit smaller so we can still have them to reference their output. And then we will open a new window and put that on the bottom here. And then we're going to want to get back into our examples, basic examples, Motoko, basic Bitcoin example subdirectory. And this project uses Git submodules. So we want to run the Git submodule update init recursive command to update the submodules. And if we are on Mac, like I am, we need to use Homebrew to install a couple different libraries. If you're on Linux or another operating system, you'll use whatever your local package manager is. But on Mac, we're going to use Homebrew and use brew install. We're going to install the package LLVM, the package bin Arian, and CMake. So we'll give those a few minutes. And once we have those installed, we are ready to deploy our example canister. So we're going to use DFX deploy. The canister is going to be called basic Bitcoin. And then we're going to pass an argument flag. And this is going to use this variant reg test since we want to develop locally on that reg test network that we set up in the bitcoin.com file. So I'm just going to copy and paste this over to my terminal, make sure that it gets formatted correctly. I'm going to hit enter. And we can see it's going to deploy the basic Bitcoin canister. So now that it is ready and it's been deployed, we can interact with it. And first we are going to generate a Bitcoin address. So in order to receive Bitcoin, we need that Bitcoin address. There are a couple different types of Bitcoin addresses, and most can be generated using an ECDSA public key. So in this basic Bitcoin canister, the code has an example that generates a P2PKH address using the ECDSA public key. So we're going to call that method of the canister with DFX canister call basic Bitcoin, and then get P2PKH address. And it looks like I made a typo. I hit W instead of 2, so mine failed. So we'll fix that typo. And now we can see that we've gotten a Bitcoin address. And alternatively, you can also use the Candid UI for this. And this Candid UI is available at the Canister's Candid interface URL, which is highlighted in green in the terminal. And then now that we have a Bitcoin address, we can receive BTC on our local network. Bitcoin uses the proof of work consensus mechanism, which means that blocks on the network need to be mined in order to have BTC be minted, since BTC is rewarded to miners as compensation for mining those blocks. On the Bitcoin testnet and mainnet, you cannot control when blocks are mined, but since we have a local Bitcoin network running, we can manually mine blocks using the following command with our Bitcoin in our Bitcoin D directory. So I'm just going to first copy this piece of code, and then we are going to need to open another terminal window. And for this one, I'm just going to put it over in the top here so we can still see everything else we've got going on. And I'm just going to navigate back into that developer journey and then the Bitcoin 27. And then I'm going to paste that command that is going to generate address or generate to address, number of blocks address. And so we'll see that I have to fill in these last 2 bits. So for example, we are going to just mine 1 block. And then we're going to go over here where we got our Bitcoin address, and we're going to paste that in. And it looks like we are running into that same error where we got stopped from running it because the developer was not verified. So we're just going to follow that same process of opening the privacy and security settings in Mac, scrolling down and hitting cancel, and then going over here, running our command again. And now if we go into privacy and security, we can see Bitcoin CLI was blocked. We're going to hit allow anyways, and then verify. And then we'll close these windows and run that command one more time. And now we'll have the option to hit open. And we can see that now we've gotten a hash of the block that was just mined. And then in the terminal window over here, that is showing the DFX start output. And so now over here, we can see in the Bitcoin D window that we've got here that's showing us the local Bitcoin logs, we can see that there is a new block, and we can see the height, it's the first block. We can see the date and the time. And then if we want to check the balance of our Bitcoin address now that we've mined that block, we can do DFX canister call, basic Bitcoin, and then the get balance method. I'm just going to copy and paste the BTC address portion at the end. And then let's see. Oh, and silly me, I copy and pasted it, but we need to replace that address with our proper address. So we'll just go ahead and copy and paste that. And that should work now. And we can see that we have what appears to be 5 billion, but this equals 50 BTC. And so remember, this is local BTC. This is not valid on the testnet or the Bitcoin mainnet. It's not real BTC. It cannot be spent or used anywhere else. And so now we mined a single block and received a reward of 50 BTC. One prerequisite before you are able to send BTC to another address, though, is that an additional 100 blocks must be mined. This is known as the Coinbase maturity rule. So to mine an additional 100 blocks, we're going to copy and paste this command back into our terminal over here. And remember this last portion here, we need to paste in our Bitcoin address. And we can see we get all of the hashes of all of those 100 blocks. And then we now have the ability to send BTC to another user. And so in this example, we're just going to use this dummy address. You can replace this address with any address that you'd like. And so we're just going to use this DFX canister call basic Bitcoin send, and then destination address is that dummy address, and then the amount in Satoshi. And so I'm just going to go ahead and copy and paste that command over here in the terminal. And we'll wait for that to process. So now we've sent this transaction and we've gotten the transaction hash, but now we need to mine a block so that the transaction that we just sent becomes part of the blockchain. Without mining a block after sending this transaction, the transaction will not be recorded on chain. So now we're going to go back to our terminal over here. And we are going to run the following command to go ahead and mine another block. And this one here, the address is already inputted, but we are going to just go ahead and use our Bitcoin address again. And then now we can use the DFX canister call command to check that the transaction was recorded. And so the address that we sent it to should now have a balance of 1 Bitcoin. So I'm just going to go ahead and copy and paste that command into the terminal. And now we can see that this address has some Bitcoin in it. Mine has more than the amount in the tutorial here, since I ran this transfer a couple of times to make sure that it was working properly. And so for me, this address now has 50 Bitcoin in it. So that'll wrap things up for today's tutorial. Please be sure to like and subscribe to the DFINITY YouTube channel if you like today's episode. If you have questions or feedback, please reach out on the Discord channel for the ICP developer journey, or reach out on the developer forum. And then we're going to begin by setting.
And so that will wrap up the demo portion of this workshop. So were there any questions, or if anybody wants to jump right in and get started building, there are some QR codes here for our developer docs, specifically the Bitcoin docs or the docs on the CKBTC token, or there's also a link to the ICP Chain Fusion Educate Bitcoin edition.
Amazing. Thank you so much, Jessie. Yeah, so if anyone has any questions, feel free to pop them into the chat. And if not, I just want to say that this workshop will be recorded. Yes, there will be more workshops. There'll be the part 2 of this on Thursday, and then another one next week. I'll be sending out email reminders and Discord reminders as well. And you should also have them in your calendars if you've signed up from the Luma. But all the workshops will be recorded and sent to you guys. Also, Jessie, would you mind sharing the slides as well, potentially?
Yeah, and also the QR code at the top is for these slides, but I can send a link to you as well.
Amazing. Yes, that would be great. And then I can send that to the hackers as well. And yeah, thank you so much, Jessie, for the workshop. I'm sure it'll be super useful for everyone participating in this hackathon. And yeah, if there's no more questions from anyone, that will be all from us today. And I look forward to seeing you guys on Thursday. Bye-bye.